Welcome to the session. Today we are going to discuss module 5 graphs and trees. In that we are going to discuss the question bank. See, first the question is, what is the Prim's algorithm? Explain the procedure of this algorithm with a suitable example. Here, Prim's algorithm is a greedy algorithm that is used to find a minimum spanning tree from the graph. Prim's algorithm finds the subset of edges that includes every vertex of the graph such that the sum of the weights of the edges can be minimized. Prim's algorithm starts with a single node and explores all the adjacent nodes with all the connecting edges at every step. The edges with minimal weights causing no cycles in the graph got selected. The step to implement the Prim's algorithm are given as follows. First, we have to initialize an minimum spanning tree with a randomly chosen vertex. First of all, we are going to initialize the minimum spanning tree with randomly chosen vertex. Now, we have to find all the edges that connect to the graph in the above step. With the new vertices, we are going to identify whatever the vertex you are going to select. From that vertex, we are going to find all adjacent edges, and from the edges, we have to find the minimum edge, and that edge is going to be added to the previous vertex which we are going to select randomly. And in the same manner, we are going to repeat step 2 until we are going to get the minimal spanning tree. First, anywhere we have to select one vertex, and this is the initial vertex for the tree, minimal spanning tree. And from that, we are going to select the adjacent edges and which is having the minimum edge, and we are going to add to that vertex, and we have to follow the same procedure until we are going to get the minimum spanning tree. That means how many edges that we are going to select, it is nothing but depending on the number of vertices minus 1. If the number of vertices are 7, then the number of edges that we have to select is only 6. So like that, we are going to repeat the process until we are going to get the required edges, and whatever the edges that we are going to attach to the vertices, and that is nothing but the required spanning tree. And let us go for the example. Suppose we are going to consider a graph. A graph is like this. So which is having 5 vertices, and of course some weighted graph, and this is going to be applicable only for the weighted graph. That means that the graph edges are given some weights. So first of all, we have to select any one vertex. Randomly we are going to select. Let us choose B is the vertex. Now from B, there are adjacent vertices. One is C will be there and one is D will be there. So among these two, which is the minimum weight? So the 4 is the minimum weight. So we have to consider the vertex D. So now we have to choose and add the shortest edge from the vertex B. And there are 2 edges from B that are B and C and D. So with these weights are then 10 and 4, then we are going to select one vertex whose weight is 4. So this is the minimum spanning tree now. Now let us go to the third step. So from where we are going to select? So either we are going to choose this D from these D adjacent vertices, or from B adjacent remaining vertices, which vertex edge corresponding edge weight is minimum, that we have to select. So here 10 will be there and 1 will be there. D adjacent is E, which is not traversed, and B adjacent is C, which is also not traversed, but the weight is 1 and 10. Among this, the weight is 1 that we have to select. So we are going to select the edge E, the edge DE, whose weight is 1, whose weight is 1. Now, let us have having 3 vertices. Among 3 vertices, then we have to find out what are the adjacent, minimum adjacent vertices and its corresponding weight of the edges. So here, B will be there, E will be there, D will be there. These are the already we traced vertices. We traced vertices, and from these vertices, we have to select the adjacent minimal edge. So among this, so this is 2, and this is 6, and this is 10. So among these 3, we have to select 2, weight is a minimum. So we are going to select, subsequently, C is going to be added. C is going to be added. So I am going to get C is going to be added in the 4th step. So after that, and BCE. So from BC, so I am not going to consider, I am going to remove. Then, so I am going to get BCE, E and C. And B, if I am going to, it is not possible to connect. And this is also not possible to connect. Only, we have only one option. Then I am going to select that edge. So I am going to select the corresponding node. Then all vertices are there, and we are selecting n minus 1 edges, that is 5 minus 4. Now the process is completed. So now we have to find out what is the minimal cost of the minimal spanning tree. Then we are going to add 4 plus 2 plus 3 plus 1. So we are going to add all the edges weights. Then we are going to get 10 units. So this is the minimal spanning tree by using Prim's algorithm we are going to get. Next, another algorithm related to finding a minimal spanning tree, that is nothing but a Kruskal's algorithm. So next algorithm we are going to consider as a Kruskal's algorithm. So I explain the procedure of the Kruskal's algorithm, and we are going to find by taking an example, we are going to apply the Kruskal's algorithm, and we are going to find the minimal weighted spanning tree. So here, so this is going to be used to find the minimal spanning trees. And now, so here what is the algorithm, Kruskal's algorithm procedure is, first of all, we have to sort all the edges from low weight to high weight. That means we are going to arrange all the edges weights in ascending order. So low weight to high weight, we are going to arrange all the weights of the edges. Then now take the edge from the lowest weight and add it to the spanning tree. If the edge to be added, creates a cycle, then we are going to reject. That means we are going to select the edges. So we are going to, while selecting the edges, we are going for the lowest weight, and we have to select that edge. While we are going to select that edge to the spanning tree, it should not form any cycle. If it forms a cycle, we should not select that. We are going to reject that edge. And the same way we are going to continue to add the edges until we reach all the vertices and the minimum spanning tree is going to be created. So this is also we are going to select the n minus 1 edges, or else we are going to select the all vertices. So by doing this, if we are going to select all the vertices, then whatever the required spanning tree is nothing but a minimal spanning tree. So here we are going to consider one example, and this is the example. And this is a graph. From this graph we are going to get a spanning tree. So spanning tree means it is nothing but a tree, and which is having all the vertices of the given graph, then that is known as a spanning tree. We can get so many spanning trees, and corresponding so many weights. And among that, which weight is minimum to select the main minimum weight, and it is a tedious task. So to avoid that, we are going to use Prim's as well as Kruskal's algorithms. Now let us go for the first step of the algorithm. We are going to write all the edges. We are going to select all the edges, and we are going to arrange all the edges in ascending order. So the lowest we are going to select. So that should be written at the first. So AB edge will be there. AB edge whose cost is 1. So we are going to select that. We are going to select that first AB. Next we have to verify which cost is minimum. So 1 is selected, then the other one is 2 is there. So 2 is nothing but DE. So we are going to select DE. And the next minimum is 3. 3 is nothing but BC. So we are selecting BC. Next minimum is 4. That is nothing but CD. So we have to select that. Next minimum is 5. So that is AE. We have to select that. Next minimum is 7. And we have to select AC. And the next minimum is 10. Then we have to 10 the corresponding edge. So now we are going to arrange all the edges in ascending order. So how many edges we are selected? 1, 2, 3, 4, 5, 6, 7 edges. So now from this we are going to construct a spanning tree. So for that, let us go for arbitrarily. We are going to select any one vertex. So one vertex means I am going to select the minimum edge. So then we are going to write this as select another option. We are going to select this first AB edge. So I am going to write AB edge. After that, the remaining is DC will be there. DC will be there. One is AB and another one is DC. So AB I am going to select in this way. And next DC is going to be selected in this way. There is no question of formation of a loop. So I am going to select that. Next, BC is 3. So BC I am going to select this. While I am going to select, no loop is going to be formed. So then 3 edges are selected. Then CD. Then the another one is CD. So CD is AB we selected and DE, sorry, not this, and this is DE. DE. Now after that, I am going to select a CD. CD is also selected. CD is also selected. Now there is no question of forming a loop. So how many edges I am selected? 4 edges I am selected. So how many edges it is having? 1, 2, 3, 4, 5, 6, 7 edges. So I need to find out 1, 2, 3, 4, 5, 6, 7. I need to find out 2 more. So now another is AE. AE if I am going to select, there will be a loop form will be there, cyclic formation will be there. So I am not going to select that. Next AC. So one is AB selected and another one is DE selected and another one is BC selected and another one is CD selected and another one is AE is not selected and next AC is also not selected and next another one is AD is also not selected. So how many vertices it is having? 5 vertices and we are going to select 4 edges and the remaining edges it is not possible to select because if it is selecting those edges then automatically the cycle is going to be formed. So for that we are going to remove all these 3 edges. With the 4 edges only we are going to find the spanning tree is like this. So this is the way that we are going to find the spanning tree and we are going to find what is the minimum weight of this spanning tree. So the minimum weight is minimum weight of the spanning tree is 1 plus 3 plus 4 plus 2. So it is nothing but 10. So the minimum weight is nothing but 10 is the minimum weight of this spanning tree. So like this, we have to find out. See here, we have to find out. Then here, we have to find out the minimal spanning tree. Then this way, we are going to apply the Kruskal's algorithm. Now, another one is, what is a Euler's graph? Explain Euler's path, explain and Euler's circuit with suitable examples. So, a graph is said to be Euler's graph. A graph is said to be Euler's graph if it is having a Euler circuit. If it is having a Euler's circuit, then we can say that the graph is a Euler circuit. Or another theorem will be there. Any connected graph is called Euler's graph if and only if all the vertices are even degree. This is a theorem. Whenever all the vertices degrees are even, then we can say that it is a Euler's graph. So we can consider in both for the definition of the Euler's graph sake. So here, one is it consisting a Euler's circuit, and next all the vertices of degrees should be even. Let us go for, we are going to consider one example. I am going to take this example, and in this example, and whether we have to find out whether it is a Euler's graph or not. So first of all, we are going to find it is containing Euler's circuit, whether it is containing Euler's circuit or not. A circuit is nothing but, it is a closed walk. While we are going to moving from one vertex to the remaining vertices, that means while we are going to considering the edges, that means it is a closed walk, and wherever you are going to start, let us say I am going to start with the vertex B, then I am going to move B to A, and next after that A to C, and afterwards C to E, and afterwards E to D, I am going to take E to D, after that, and E to D, and another one is next D to C, next C to B. So from where you started, and we are going to move all the vertices, and while we are going to reach the same vertex, it represents only a closed walk. So any closed walk which is consisting all the edges of the given graph, then that graph is, circuit is, closed walk is known as a Euler circuit. Euler circuit is nothing but a closed walk, and any closed walk which is having all the edges of the given graph, then that is known as a Euler circuit. So this graph is having Euler circuit, so we can say that it is a Euler's graph based on this. And next, based on this definition, each and every vertex degree, vertex A degree is 2, vertex B degree is 2, vertex C degree is 2, E degree is 2, D degree is 2. So all vertices degrees are 2, then we can say that it is a Euler's graph. This is a Euler's graph. So in both ways we can say that the Euler's graph we are going to use to find a Euler's graph. We are going to use these two definitions. And now one is a definition and another is a theorem. Based on the theorem we are going to calculate. Now Euler's path. What is a Euler's path? Euler's path is known as a Euler's trial, or Euler's, it is known as Euler's trial or Euler's walk. It is an open walk, strictly saying it is an open walk. So beginning vertex is not equal to ending vertex. Open walk is. So here if there exists a walk to the connected graph that visits every edge of the graph exactly once, with or without repeating the vertices. With or without repeating the vertices, such walk is known as Euler's walk. Such a walk is known as a Euler's walk. So here, while just moving, it has to be traced all the edges only once, and while you are going to concentrate on the edges, while you are going to visit every edge of the graph only once, with or without repeating the vertices. With or without repeating the vertices. If you are going to without repeating the vertices, then that is known as a Euler's path. And if it is any vertex is repeated, then it is known as a Euler's trial. Then let us go for the Euler's path. Now, here the first one is a Euler's path. So, let us go for, this is a open walk. It is nothing but a open walk, a connected graph that contains all the edges of the graph. Then the trial is called a Euler's trial. So now let us go for, this is, I am going to move starting with any one vertex, and I am going to move like this. Then I am going to, next one is, we are going to move to this one, and we are going to, or else, so once we are going to trace out this as, let us go for BC, and next BC, next CD, we are going to take CD, next we are going to consider DB, and next we are going to consider AD, BA, then we are going to consider AD. So you started from B B to C you traversed. That means whenever if you traversed, edge 1 is completed. Now C to D if you traverse, edge 2 is completed. Then D to B if you are traversed, D to B, edge 3 is traversed. And next B to A is traversed, edge 4 is traversed. And A to D is going to be traversed, edge 5 is traversed. And initial and ending vertex is not same. So we are going to call this as, strictly speaking, it is nothing but a Euler's trial. In this, we are going to say that vertex is repeated. So in general, we are just discussing about Euler's path and Euler's trial are in the same manner. So for that reason, we are going to say that it is a Euler's path. Now, another definition. So another graph. So here, BC is BC, and next another one is CD, another one is CD, and another one is DF, another one is DF, and another one is FB. Okay, next BE, and next ED, and after that DA, then again AB. So all the edges are covered. So we can say that this is also a Euler's path. And next, here it does not possible to cross all the edges only once. And here if I am going to move, let us say, if I am going to move to here, and twice I have to traverse to take over the other edges. So this is not a Euler's path. And next, this is already discussed, Euler's tour or Euler's cycle, and this is Euler's circuit, and the same we were going to discuss earlier, and the same thing. And now we are going to find what are the adjacency matrix of the following graph. So let us go ahead. The graph is given as, so here we are going to take it as, some of the vertices and I am going to consider a graph is like this. So it is V1, V2, V3 and V4. Then the edges are, let us say this is E5, E1 edge, and next another one is E2 edge and E3 edge and E4 edge, E5 edge. For this we are going to find the adjacency matrix. So here adjacency matrix means we have to write all the vertices V1, V2, V3, V4 and the corresponding V1, V2, V3 and V4. Whenever V1 to V1 there is no edge, 0. Whenever there is an edge, we are going to take it, the corresponding value is 1, otherwise it will be 0. Now V1 to V2 there is an edge, so I am taking that as 1, and okay, V1 to V3 there is no edge, 0. V1 to V4 there is an edge, 1. Similarly, V2 to V1 there is an edge, V2 to V2 is not there, V3 to V3, V4 to V4 is not there. So then V2 to V3, V2 to V3 there is an edge, so we are going to take it as 1. V2 to V4, V2 to V4 again there is an edge, and next V3 to V1, V3 to V1 there is no edge, and V3 to V2, V3 to V2 there is an edge, and V3 to V4 there is also an edge. Then V4 to V1 there is an edge, V4 to V2 there is an edge, V4 to V3 there is an edge. So now the adjacency matrix is nothing but A as, we are going to take it as 0, 1, 0, 1, then 1, 0, 1, 1, next 0, 1, 0, 1, then 1, 1, 1, 1. This is the adjacency matrix. Now, if you are going to find out, if you are going to find A square, what is A square and A cube? So, A square is nothing but A into A of path length is 2, then we are going to consider, then simple multiplication we are going to do, 1, 0, 1, 1, and 0, 1, 0, 1, and next 1, 1, 1, 1, and the same thing we are going to write V4 as 0, this as 0, and this is also 0. Then we have to take 0, 1, 0, 1, then 1, 0, 1, 1, 0, 1, 0, 1, 3 ones and 0. Then using the matrix multiplication, then we are going to get this as 2, 1, 2, 1, next 1, 3, 1, 2, then this is 2, this is we are going to have 2, 2. So some matrix we are going to get. So it is, so let us go for the, let us see this, 0 into 0, 1 into 1, 1, then this is also 1 into 1 plus 1. So next, like this, 0 into 0, 1, next 1, 0, then it is 1, then another one is just a simple multiplication, then we are going to get A square, that is nothing but 2, 1, 2, 1, 2, 1, 2, 1, and 1, 3, 1, 2, like that we are going to get. We are going to get A square. Now similarly you can write A cubed as A square into A square into A. Similar process if you are going to get, then we are going to get 2, 5, 2, 5, then 5, 4, 5, 6, like that we are going to get 2, 5, 2, 5, and 5, 5, 5, and next 4, like that we are going to get. So from this, what we are going to observe, A square or A cubed, then this is nothing but a suppose first one, if you are going to say V1 to V1, V1 to V1, the path length is 2. Path length is 2. So then we are going to consider if there is a path from V1. So then V1 to V2, there is a path, and like that, the path lengths only we are going to find out from A square and A cube, like that. And now we are going to verify the next one is whether the following graphs G and H are isomorphic or not. So here, we are going to consider the graphs are V1, V2, V3, V4, then it is V5, then it is V6, then we are going to add. So this is one graph. Let us say this is Z, and the H is, let us say, we are going to take it as U1, U5, then it is U4, then it is U3, then it is U6, and then U5 to U6, and U1 to U2, and U2 to U3. So this is H. While we are going to see that whether the graphs are isomorphic or not, first we are going to verify the number of vertices. Second, we are going to verify the number of edges. Then after that, we are going to verify the adjacency is preserved or not. And or else, we are going to consider, let us say, what is the degree sequence? What is the degree sequence of all the vertices? Now, the number of edges. So, number of edges of G is how many number of vertices? First of all, number of vertices. So how many number of vertices in G? 6. The number of vertices in H is also 6. And the second one is number of edges. So number of edges in G is equals to 1, 2, 3, 4, 5, 6, 7. And the number of edges in H, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Now, what is the degree sequence? So, let us say here F is a mapping from G to H. I am going to map while after calculating the degree sequence of the graph G and H. So, what is the order? What is the degree sequence? So, here degree sequence G is, so first is 2, when if you are going to consider for the vertex V1 it is 2, and for the vertex V2 it is 3, for the vertex V3 it is 2, for the vertex V4 it is 3, for the vertex V5 it is 2, for the vertex V6 it is 2. That's all. This is the degree sequence. This is we are going to take in the same order. Now in the that means V1, V2, like that we are going to take. And for H, and we are going to consider what is the degree sequence for U1. U1 is 1, and U2 is 2, and U3 is 3, and U4 is 2, and U5 is 3, and U6 is 2. Now I have to map. What is F of V1? F of V1 is equals to U. 1. And F of V2 is 3 will be there. I am considering this is for map to U3 vertex. Then F of V3, third vertex is map to 2. And F of V4 is 3, and it is nothing but U5. And this is U2. Then, so F of V5 is it is true, I can take it as a U4. Then f of V6 is 2. That is nothing but here U6 is also 2. U6 is also 2. So what is the mapping is V1 to U1 and V2 to U3 and V3 to U2 and V4 to U5 and V5 to U4 and V6 to U6. So under this mapping, we can say that the two graphs are isomorphic to each other. Now, let us go for the other example. The pairs of the given below are isomorphic or not. Let us consider, I am just taking the one graph is like this. We have to consider. So here A, B, C, D, E, and next another one is A dash, and next this is a C dash, and this is E dash, then it is B dash, and this is D dash, and this is E. So this is graph G and graph H. Whenever if you are going to consider a complete graph with 5 vertices, so what we are having, see here, this is the graph with 5 vertices, and next Kurtoski is first graph, and you observe this is the outer circle, outer curve, and this complement we are going to get inner, and the inner one is nothing but this, and its complement is this. So for this complement is this, and for this complement is this. So from this also we can say that they are isomorphic, or else we can say that how many number of vertices it is having, 5 vertices it is having. G is having 5 vertices, 1, 2, 3, 4, 5, and H is also having 5 vertices. And the number of edges are 1, 2, 3, 4, 5, and here also 1, 2, then 3, then 4, then this is 5. So both vertices and edges are same, and degrees if you are going to consider, sequence if you are going to consider, each and every vertex degree is in G it is 2, and each and every vertex degree in H is also 2. So we can say that both graphs are isomorphic to each other. So G is isomorphic to H. So G is mapping to the function f is from G to H, and here in whatever the manner that you are going to map, f of A is equals to A dash. F of A is equals to A dash. That means E to F of E. I am going to take it as, I am just taking B. F of B. So here A is adjacent to B, then here A dash adjacent to D dash. And next another one is F of E. I am going to take it as another adjacency is C dash. And next F of D is, so it is nothing but C dash adjacents. So C dash adjacency is nothing but E dash, and F of C is B adjacency. So it is nothing but F of C is D dash. So D dash adjacency is B dash. G dash adjacency is B dash. So A B dash is over, B dash is over, C dash is over. This is not D dash, and it is nothing but A B. This is B dash. A dash, B dash, C dash, D dash, E dash. So all are over. So under this, we can say that both graphs are isomorphic to each other. Anyway, we can say that this complement is this or this complement is this. From that also we can say that both graphs are isomorphic to each other. So with this, I am concluding. Somehow we have discussed only some of the questions in 5th module. With this, I conclude this. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.